Okay, now the suspense has been building, and we're finally to the part of the verdict. Okay, so remember, a high p-value says the data is likely given the null hypothesis. We never say that something is innocent or true. The only thing we can do is reject things, or in this case, fail to reject. All right. Sometimes when we have a high p-value, we're going to say the null hypothesis is retained. The interesting part happens when we have a low p-value. That says the data is unusual given our null hypothesis. The data is not consistent with it. So we say we reject the null hypothesis because the p-value is less than, or it is this much, whichever bar you set. So what p-value should we use? Typically, we use a p-value of 0.05, but you may want a more stringent p-value if you're rejecting a long-standing hypothesis, something that everybody accepted was true. You might want to be more critical. You may want a more stringent p-value if there's risk in going with an alternative hypothesis. So you may want to be really sure before you invest millions of dollars, or maybe you start experimenting with medication on people. You may be less stringent with the p-value if you're more willing to accept false positives, or if there's some benefit, that there's little downside to trying your alternative. And another thing to take into account when picking your p-value is how important is the issue we're testing. So now we're going to go ahead and state our verdicts for our 3 examples. So going back to the smoke detector, we had a p-value of 0.0038. That means if 90% of the homes in the city contained smoke detectors, there would only be a 3.8% chance of finding 376 out of a sample 400. That's pretty low. So we're going to reject the null hypothesis that p is 0.90. The p-value is very low, making it unlikely that the observed results can be explained by sampling error. We reject the null hypothesis. There is strong evidence that in this city, more than 90% of homes have smoke detectors. Okay, now let's get to the M&Ms. So here our p-value was 0.4413. So if the actual percentage of M&Ms is orange, then we could find values 21 out of, a p-value of 0.172 or further away 44% of the time, almost half the time. So that's not very convincing. So we fail to reject H0. We're going to say, for now, we're going to go work with this, that p is 0.20. So there's no evidence to suggest that the proportion of orange M&Ms differs from the advertised 20%. How about our unfit teens? We had a p-value of 0 there. So we're definitely rejecting the null hypothesis, and it seems pretty convincing evidence that more than 30% of adolescents have a very poor fitness level. All right, one last thing before we move on is there's a better confidence interval for proportions. So what is this? It's a little strange. What you do is you add 4 phony observations, 2 for successes and 2 for failures. And you use an adjusted proportion. So instead of just your y over n, it's y plus 2 over n plus 4. And so we write our n with a little tilde here is n plus 4. All right. And then we modify the interval using the adjusted values and the margin of error. And our new interval is this. Okay. The reason they use it is they found that when we do our 95% interval, it really doesn't capture it 95% of the time. If we want to do this interval with a 95% confidence level, that actually is much closer to catching it 95% of the time. So just a very strange little method if you want to be a little more confident. Okay, last bit. What can go wrong? Really 2 things to, there's a whole chapter next unit on what can go wrong, but let's hit these 2 main things. Don't make your null hypothesis what you're trying to prove to be true. We can't prove a hypothesis is true. We can only reject it or fail to reject it. And of course, don't forget to check your conditions.